Well, folks, I want to give you a little bit of background about why we undertook the study at Little Thompson Observatory that is published in your proceedings. I'm not going to go through the technical information from that report because it's kind of late in the day. Some of you might be interested, others probably would not be interested in the technical information on it. I'm going to give you sort of an overview, I guess, of why we got involved in the study and then jump to our conclusions out of it. Basically, our observatory got involved in radio astronomy as an outreach tool for K through 12 students. We had been fairly successful over about a 20-year period of time in engaging kids in the community in optical astronomy. About a half a dozen of us who were regular volunteers there were, number one, hams, but secondly, we had some degree of equipment at home that we had dedicated to radio astronomy, and we wanted to sort of share that. Our board was skeptical that students would accept radio astronomy either as a legitimate field of study or something that would interest them. And I think I shared last year with many of you that on our opening night, we were just about mobbed with kids interested in what they saw on the screen. We project radio meteors on a screen like this in our auditorium. The kids were absolutely fascinated, far and away more enthusiastic than we ever imagined that they would be. So that gave us the courage then to go into more advanced forms of radio astronomy, and through Skynet Junior Scholars, we're able to remotely use the 20-meter dish here. Well, that is sort of background. What we were doing last year and are continuing on through this year is working with one of our local high schools during the school year, providing mentors to a physics class, STEM students, on original investigations. Last year, the investigations had to do with H1. The students this year decided they wanted to study meteors. And we were working with them, selecting students who would, during the summer, become interns, STEM interns at our observatory, but trying to help guide them through the development of research strategy with meteors. And the strangest thing happened. December 31st, we lost the signals that we were counting on to provide reflections from the meteor plasma trails. So I'll go into some detail on that in a few minutes, but that's the background of why we undertook this study. So one of the things we do when the students come in and we're talking to them about meteors is we explain what a meteor is, what a meteorite is, and one of the little tricks I do is they have everybody do this, because this is a meteorite, and they can now say legitimately they have caught a falling meteorite in their hand. So if anybody hasn't seen one, that's a metallic meteorite. They come in stony, metallic, several other different classifications. And for anybody who's never held a moon rock, here is a sand-sized piece of the moon. So all of these things are the things that are up in the sky that the public calls shooting stars, we call meteors, and physicists have many, many different other classifications for what is happening up there. But the challenge that we see is continued study, particularly by amateurs, of this phenomenon that's occurring in the upper atmosphere. Traditionally, just about everybody studying meteors and meteor trails have used what's called bistatic radar. You have a transmitter over there, completely independent of the transmitter. You have a receiver over here, 500 to 1,000 kilometers away, the angles work just about right for getting good reflections from meteor trails. The huge advantage of that from the researcher standpoint is somebody else pays the electric bill for the transmitter. And that's a great advantage. All you have to worry about is your receiving side. But the best radio frequency range for meteors is in the low VHF range, somewhere between 35 and 75 megahertz is ideal. You can go lower, you can go higher, but that's sort of the ideal range. But worldwide, the free transmitters are beginning to disappear on us in that frequency range. A lot of technical reasons. In this country, for instance, digital television, the transition to digital TV caused a major disruption. And indeed, that's what happened to us on December 31st last year, because our students were listening to transmissions bounced from meteor trails, transmissions from Calgary in Canada and Juarez, Mexico. And on December 30th and 31st, both of those transmitters went off the air. So we began a desperate search then for what other good signals are out there that we can take advantage of. So one of the things I looked into is the entire question of what is it we're looking at. The traditional model of meteor scatter, as most people would refer to it, is a meteor enters the atmosphere. It leaves a trail of plasma behind it, caused by two different things, ablation or burning off of the meteor substance itself, and heating of the upper atmosphere, or in the ionosphere, and creating ions from the particles in the air. That was the traditional explanation that seems to work, and everybody in the world who studies meteors has made their calculations based on that model. Well, sort of interesting. Mears Oppenheim at Boston University and a group of graduate students are challenging that theory. And unfortunately, Boston University has a policy of copyrighting everything. And we can't get copies of this paper without paying about $165 per copy. Now, I have read it because a friend of mine had it, but we just couldn't run it through a Xerox machine and share it with anybody. But essentially, his theory is that we do have it all wrong. And the angles that we have used to calculate reflections just don't work anymore. So his theory, in a nutshell, is that meteor enters the atmosphere, just like we always think, creates this cone of plasma behind it, but that's not what's reflecting the radio signals. What reflects is a secondary action that occurs, that this plasma trail attracts opposite charged ions from the region around it in the upper atmosphere, and it creates not a cone or a cylinder, but a sheet, a flat sheet of about a half a mile wide, maybe, and as long as the meteor trail would be. So it could be quite long, it could be quite short. But his complication in all this is that the angle of this sheet that's been created is highly dependent on the magnetic line of force at that particular altitude and latitude. So in Denver, where I'm from, the magnetic lines of force are coming down at about an 8-degree angle to the Earth. So these sheets, according to his theory, will all be tangent to that line. So it now is more like a mirror reflection in the sky. If the mirror is tilted like this, we're going to get a much different reflection pattern than if the mirror is tilted like that. And so, not to give away all of his secrets, we just need to do more study about meteors to confirm or dispute his theory. Now, he's using a very powerful monostatic radar, so he's sending up his own signals to try to prove his theory. But it seems that now is the worst possible time for us to start losing these signals of opportunity that we as amateurs and even university researchers have depended on for so long. So I started looking around at what other people are using. Well, in Europe, the Europeans are really and truly lucky. They have some good signal sources, plus a nationwide intentionally designed system to study meteors. The Graves radar, and that's an acronym, is operated by French Ministry of Defense. It's a very nice radar system, very powerful, around 140 megahertz, but it provides backscatter reception for meteor trails throughout most of Europe. So even the folks in UK get really, really good meteor trails from the Graves radar. Belgium has the Brahms system, which is the Belgian radio meteor system. I go into some detail on how their system works in the paper, but just know that this is a partnership between the Belgian government, several universities, and lots of amateur radio astronomers to set up a network of fairly low power transmitters around 40 megahertz. So they picked the ideal frequency for it. And with known transmitter powers, precisely known locations of transmitters, it now becomes possible to start doing some of the math needed to confirm Dr. Oppenheim's theories. So they're in a position to do that much better than we are in the US. And then, of course, they have digital TV and VHF, FM as we do. Here in North America, though, we've really lost some good signal sources over the last 10 years. Space fence radar was a little high in frequency, but good power levels. That was shut down. Analog television, which was almost ideally suited for this, on the lower channels, channels 2 through, say, 4 or 5, was in a good frequency range. Megawatt transmitters, or at least effective radiated power of megawatts, generally aimed at the horizon. So for the distances that are ideal for radio meteor work, that was just about perfect for us. But the transition to digital television there were a couple of things that happened. Channel 2, or stations that claim to be Channel 2, are not necessarily broadcasting on 54 megahertz anymore, the way they used to. Many of those Channel 2 stations are now actually UHF transmitters that are allowed by the FCC to continue identifying themselves as Channel 2, and when the television scans for its local signals, it will display on the screen as Channel 2. But the actual broadcast frequency is UHF. It's very complicated and kind of works against what we tried to do here. But there are still a few transmitters down in the Channel 2 through 4 or 5 range. And in the paper, I give you a link to the FCC website where you can research the actual broadcast frequencies as well as the precise locations of the transmitters. Another system that we're losing is the Meteor bounce system that was operated on the East Coast through Mississippi Valley for flood monitoring. It was a system, the acronym is SCAN or SCAN, around 40 megahertz, not necessarily high power, but a system that was designed to use meteor scatter as a communications mode. That has now been shut down. I think the very last transmitter went off the air very frequently, or very recently, And what they've done is they've simply converted those to cell phone digital networks. This is a much cheaper option. So this is what the current signal status is in North America. Tried to be as descriptive as possible in the legend down here. Analog TV was just about ideal. You know, I think most of us who've done this would have said that was an excellent signal source. There are a few Canadian AM analog stations still on the air. There are a few in Mexico, but none of those are high-powered stations. And both countries have indicated that they will be shutting those down in the near future. So we can pretty much scratch off analog television. Digital TV, the more we have used that waveform, the more useful it is. And I'll have a graphic here in a second that kind of describes what to do. But the concern, the long-term concern, is that the waveform may change one more time. And if the trade publications for the broadcast industry are correct, that change will just about eliminate the usefulness of digital TV signals for us. FM broadcasts, those of you who were at the Prescott conference saw an excellent presentation by one of their astrophysicists there on how he is using FM broadcast for meteor studies. It really is a successful approach. In the western states, there's sort of their version of the flood warning system. It's called SNOWTEL. It uses remote sensors throughout the mountains to gauge snowpack and meteor bounce communications out of those remote locations back to two central processing points. Those signals are still on the air. They're not terribly powerful, but if you're in the right location, it's a useful signal. So folks in New Mexico, Colorado, Arizona are about the right distance and can get some useful meteor returns from that. I did then a survey of the navigational aids that is used for aviation in the country. There are one or two that may hold out promise. The system of outer markers, as they're called, operates on about 75 megahertz. Not a lot of power. Most of their signal is directed perfectly toward the zenith. So they're fairly good for checking aircraft reflections, not particularly good for meteors. But it is useful if you have nothing else. I was talking about the waveform used for digital broadcast. It's a 6 megahertz wide channel allocation. Previously with analog, a huge amount of the power went into the carrier signal that carried the modulation. With digital, it's entirely different. The power is consumed in this digital waveform here, and that is almost entirely useless for our purposes. Nobody has yet found a way of extracting refracted signals out of that in any useful way. What we do use is a very small, very narrow thing called a pilot carrier. And it costs, in electricity, it costs probably about $50 an hour to transmit this pilot carrier. Well, for the 24-hour-a-day stations, that amounts up over a year's time. So there is an engineering challenge out there to reduce the amount of radio power being wasted in this pilot carrier. Maybe get it down to here, just a few, maybe 3 decibels above this. All they need is just something to set the frequency so that everybody will lock in on this waveform. So there's a big push to reduce this power. Well, this is what we're using. It'd be nice if they'd increase the power there instead of decrease, but they're not going to. So with this in mind, trying to think far into the future as to what we're going to do as a community, if we just sit back and let technology take its course, we may lose, in this country at any rate, all of our useful signals. So a question that I guess I would like to raise is, what if we took charge of this ourselves as a community? What if we followed, for instance, the Belgian model, this Brahms-like system, and we built it here in North America? You know, a partnership of individuals, universities, organizations like SARA, maybe the folks in Huntsville, you know, just a true partnership of people who are committed to doing this sort of thing. Get started as a proof of concept using 6-meter amateur bands. Those of us who are licensed could do this afternoon legally. I mean, our license covers doing this. But long term, work with the FCC to get a 49 megahertz industrial, medical, and scientific band authorization with licensed transmitters. We would be causing no interference to anybody in the world, because this has been pretty much an abandoned frequency. Those of you who are of my vintage remember the old cordless phones, the first cordless phones we had with the pull-out antenna that was about that long. That's what that was, the 49 megahertz IMS band. And pretty much it's available for licensing right now. So that's something that may be worth thinking about over time. Is it something SARA would be interested in subscribing to? Is it something that you as individuals might support? Or is it just more trouble than it's worth? But we have the model to follow. The Belgians have it worked out, the costs, the operating systems. So really, all we got to do is just study their approach and see if it might work for us. This is an example of an existing ham radio beacon in Albuquerque. We received in Denver. The signal is interrupted here because of the nature of the beacon. They're sending out Morse code, and it's not a continuous transmission as we would like to have for our system, but it gives you a good example of aircraft reflections here. And when we look real closely, there are a few things in here that appear to be meteors. We need to do a better analysis of it, but at least in terms of proving the concept, we're finding that a fairly low power, this was a 25 watt beacon in Albuquerque on that frequency, is giving useful returns in Denver. It's a little too close for really good meteor work, but it would work if there's no other signal source. And again, if we were in charge of these beacons, we wouldn't have this signal that comes on and off. We would have a continuous transmission. So this is my suggestion to the community, is that we find ways to prevail, take charge of the technology. And if these studies are important to us, and I believe it's important to us as amateur astronomers, as well as it's important to geological sciences to know more about meteors, know more about the dynamics of what's happening. I think we can continue for a long time to make meaningful contributions to science if we can stay ahead of these technological changes. So that's it. Questions? Yes, sir.
The Boston U paper, was there any result from that would help us to determine an ideal beam angle if we were to set up a 6-meter beacon?
Yes. If we did a planned system and you were in New Hampshire and let's say Chip Sufficici, who runs a live meteor streaming online site, by knowing your locations, you could calculate where the reflecting plate would have to be in the sky in order to have that path completed. And so then you each could adjust your antenna height as well as directivity, elevation on it to take advantage of that.
I'm just thinking if you could optimize that to
You
run
could.
lower power.
Exactly. You're exactly right. Yes?
My question is, has anybody thought about using the digital TV signal in a different way? It looks to me like you've always been using total power.
Right.
And then if we look at the light distortion, you might be able to see your effect you're looking for.
That is quite possible. I'm not aware that anybody has been successful in doing that. I know a lot of people have tried to figure out a way,
Yeah.
but it certainly is worth a lot of effort to find out, because the signals are there.
Right.
It's just a matter of extracting something useful.
Two signals canceling each other, just like an interferometer. You just
Yeah.
saw about.
Yeah. Yes.
So by running this website, livemeteors.com, for quite a long duration, almost 2 years, I can say that not only this what's going on, the TV stations that are turning off and the sources disappearing are a reason for having this network of beacons or powerful or less powerful sources controlled by us, but we need a scientific method to count for meteors, to measure the Doppler shift, to account for the amplitude and all sorts of measurements that we can do. And there is no other way other than looking for sources that are under our control. A TV station that is in Ontario, in Canada, is maybe good enough for some quantitative measurements. We can measure what's going on there. We can show that the meteors are there. And public may be enthusiastic about that. But when it comes to make quantitative measurements, you need to know what the power station is. You need to know when the station is on or when it's off. You need to know the type of the antenna, what was going on that remote side. And we cannot control that. So this is another endorsement for this type of approach that we as a group or as AWRL or SARA or universities can support this network and have meteor detection powered by that.
Good observation, Chip, I think. And, I neglected to put Chip's website in the paper. I intended to, and it was just one of the things I didn't put in there. So give them your website again.
www.livemeteors.com.
And that's for those of you who may not currently be doing any meteor work but are interested, that's a good introduction to it, because you can actually see his receiver site and see and hear, I believe, exactly what he's receiving.
Yeah, so currently the website is looking at Ontario TV station, I forgot the name exactly, and there is 99% chance that that's the station. However, during sporadic events, I heard some other sound because I was able to listen to the audio carrier, and I heard Spanish. And for me, during sporadic, I was looking for Cuba or some other South stations. Anyway, if Ontario is gonna turn off soon, then the website will be pretty much dark because there's no other source. That powerful and good for the
Yes.
Have you ruled out VOR stations?
No. In fact, I did a survey of VOR. VOR, they're a little high in frequency to be ideal. But I did capture some meteor returns from a VOR. And the high altitude VORs are the ones that we want to focus on. And I put a link in the paper for how you find those through basically the commercial flight planning world. The high altitude VORs are more powerful, much more powerful than low-altitude VORs, and their signal is aimed more at the horizon, whereas the lower-powered stations are not trying to reach out beyond 50 to 60 miles, for instance. But the long-range VORs, we want to beam toward the horizon. So, but again, they're, the waveform is about ideal for us, but they're a little high in frequency to be ideal. You're up at 115 megahertz and higher. Yes?
What kind of funds do you think such transmitter will need? What would be the power, minimum power, and antenna or equipment, do you think?
Yeah, just doing rough calculations. Ideally, a transmitter between 250 watts and 500 watts would be the most you would ever need. The Belgian system is depending on a lot of 100-watt transmitters, so amateur-grade transmitters. Of course, they have to take continuous operation, so power supplies and those things have to be modified. Generally speaking, in Europe, they're using 3 to 5 element Yagi beams, which can be home built. So I'm thinking a good transmitter station could be installed for under $1,000. Negligible operating costs. You always have maintenance and you need a power bill, but $10 a year, $20 a year is going to cover the power bill. And receiver sites would be no different than what we're doing now. Dongles work just fine for this. A $12 dongle works beautifully. AirSpy does better. Raspberry would be perfect. So I think it'd be, to answer your question directly, a very low cost system. Yes?
How many of these sites would be required for the CONUS?
Probably 3 to 5 transmitter sites ought to adequately cover the entire country. To sort of put a transmitter in each region, and then that would be supporting people not in that region, but 500 miles to 1,000 miles away. So if you had one, for instance, in North Florida, that would give good signal coverage up to, Washington, D.C. north, up through New England, out to Chicago, and then one mid-continent. So probably 3 to 5 would do it. Yes?
Would there be a way to use two-way communication? In other words, have a sort of a adaptive system where you look at something, it's fairly weak, it has poor signal threshold, and you make a guess, and somebody steers an antenna, a phased array, power control, automatically goes, sort of the whole system is two-way, and then it's more energy efficient.
Well, it very well might be. That is the concept that both SCAN and Snowtail have. One station sends out a pilot signal, it's always transmitting. When the remote site hears that signal, it knows there is a path, and so it sends out a data burst to the main station, the control station. And very effective, runs 24 hours a day, good data throughput. So we could do something similar. I think the technology already exists. Just going to
What about some of the existing ham meteor scatter type stuff using digital modes? That's basically be beaconing with that.
Yeah, it really is. Yeah, I've monitored that now for about 2 or 3 years. Done a lot of meteor scatter work using some of Joe Taylor's software. Very, very reliable communications, but everything is hit or miss, literally, with that, simply because stations are turned on, turned off, people go on vacation, and so doing it on a regular basis, and as Chip mentioned, getting some valid, scientifically valid data out of it just doesn't work right now. Not that you couldn't design a network that would do that. Yes?
What's the technical challenge to using the 115 megahertz VOR? Like, why is that less ideal, and what would you need to make it as
Oh,
ideal? Choose a better receiver.
Just a matter of the reflectivity of the whatever is up there, either the sheet or the cone, does better with low VHF. It will work up through there, but it takes much more transmitter power to get the same reflection on higher frequencies.
Also produce a lot shorter bursts. 50 megahertz, if you listen to Meteor bursts on the amp bands, they're typically 5 seconds long, stuff like that. And 2 meters are lots of times a second long, so 150 megahertz is going to be somewhere in between. You won't have a long, easy to detect burst.
Good. Okay, thank you all, appreciate it.